Hello, welcome to 7-2. We are going to talk differentiating exponential functions, and in the second video we will integrate exponential functions. And what we're going to be focusing on mainly is base e, but again we'll be incorporating different types of bases along the way as well. So with that, we'll go ahead and start off with base e, so e to the power of x. And here, kind of as an intro to help you kind of discover the differentiation rules, it says use your calculator to graph e to the power of x. So we'll bring up our calculator, we'll graph e to the power of x, and be careful, you just punch in e, it's going to treat it as a as a constant, okay, instead of the actual value of e. So we'll use e to the power of x, and we'll go ahead and graph it. There's e to the x, and now I want to graph a second function, and I want to graph the derivative of e to the x. So I'm going to go down here next to the book, the derivative with respect to x of e to the power of x. And what do you notice? Hey, it's the same exact function, and that's what makes e to the x really, really nice. When we take the derivative of e to the x, it is just e to the x, right? And I think there's some great memes out there. There's the Spider-Man memes where it's like e to the x, and it's like, hey, e to the x, and the derivative of e to the x, hey, it's the same guy. Okay, so I know I'm lame, right? But we also have the chain rule too with e to the x. So if the power is like a function of x, then you have to multiply by the derivative, okay? So be careful, we have the hook on or the chain rule, so we'll look at those. And then if we have different bases as our exponential function, then we have our hook on factor is the natural log of that base, okay? Or ln of a, if a is our base, okay? And then again too, if our exponent is a function of x, okay, if there's more to it than just x, then we have to again multiply by the hook factor or the derivative of that power. Okay, so let's go ahead and look at some examples. So number one, it says differentiate y equals e to the power of x squared minus 3x. So in this case, our exponent, right, is a function of x. There's more to it than just x. So if I want the derivative, okay, so the derivative of e to the x is e to the x. So here I'm just going to copy this down, x squared minus 3x. But here I have the chain rule since it's more than just x. So I'll multiply by the derivative of my power. So that is 2x minus 3. And we're done. That's it. Example 2. G of t equals e to the power of negative 3t. I want to just first rewrite this. Let me switch colors for you. I'm going to rewrite this as e to the power of negative 3 times t to the power of negative 1. Okay, so g prime of t is equal to, okay, so again, I have e to the power of x, okay, so the derivative is exactly the same, negative 3t to the power of negative 1, okay, or actually, sorry, I want to write it like this, negative 3 over t, okay, times the derivative of the numerator. So the derivative of my power. So the derivative of the power would be 3 over t squared. Okay, all right. Example 3. Example 3, again, I'm going to rewrite this. This is 3 to the power of v to the power of 1/2. So my derivative, f prime of v, notice this is not base e, so it's not just e to the x, right? So I have to go ahead and multiply by the natural log of the base. So I have 3 to the power of root v times the natural log of 3 times now the derivative of my numerator, or my power, which is 1/2 v to the negative 1/2 power. Okay, so there is the derivative. Okay, so just note the different types of chain rules and hook-ons that we have. Okay, just a basic example here. Sometimes you might see this. Okay, they might say, what is the derivative of e to the x? Okay, and the answer is e to the x. So very foundational example there. All right. Number 4, it says find the relative extrema of f of x and then list the points. Do not use a calculator. So if I want the relative extrema, remember that I'm going to have to go ahead and I'm going to have to take the derivative. I need to know what is f prime of x, and I'm going to have to set it equal to 0. So f prime of x, notice I have two pieces here. I have a negative x, and then I have an e to the power of negative 2x squared. So this is product rule, okay? So I'm going to take the first times the derivative of the second. So negative x times the derivative of the second, which is e to the power of negative 2x squared, times the derivative of the inside, or derivative of the power. Okay, so that would be negative 4x, okay? Plus, now, so I'm going to do the other part, right, which is the derivative of the first, so negative 1 times the second, so e to the power of negative 2x squared. Okay, and again, I want to set this equal to 0. So what I'm going to do is I'm going to go ahead and factor this. I'm going to pull the e out, and I'm going to take a negative with me, right? So notice there's two negatives here. So if I factor out a negative e to the power of negative 2x squared, I still have a negative 4x, and then also this other x, so negative 4x squared. Over here, if I factor out a negative e to the power of negative 2x squared, I just have a positive 1 left behind. Set this equal to 0. Okay, so I'm going to factor this. I'm going to find my critical values, and those will be the x locations of where I have a relative extrema. So note, here I have negative e to a power over here. This will never be equal to 0. Okay, that's a constant, that's a value. So that's not going to yield anything. Then I have negative 4x squared plus 1 equals 0, which gives me negative 4x squared is equal to negative 1. X squared is equal to 1/4. So x is equal to plus or minus 1/2. All right. So I'm going to go ahead and I'm going to bring over my f prime number line, which I know you guys love. Right now you might be having panic attacks. I hope you're not. I'm going to put those critical values, negative 1/2 and 1/2 on my number line. Now, what I need to know is I need to go ahead and test. Where's my function increasing? Where is it decreasing to know, is it a max? Is it a min? Like, what's going on? So I'll go ahead and I'll plug in negative 1 is a good number, right? So I want to know, is f prime increasing or decreasing? So I utilize f prime, okay? Which is right here. Okay, so I can go ahead and plug this in. Now, if I plug in negative 1, I'm going to get negative value. So that would be a negative e to the negative second. Okay, that's negative. And then if I plug in negative 1 in for negative 4x squared plus 1, that is going to be a negative. Okay, so this becomes a positive. So I know my function f prime is increasing here. Then I'm going to go ahead and I'm going to check 0. F prime 0. I'll plug that in. Okay, and when I plug that in, I get a 1. So 1 times, and then over here I get it's a negative 1. Negative 1 times, when I plug in 0 for x, I get a positive 1. So this is a negative. Okay, so my function's, my function's decreasing there. And then I'm going to go ahead and check 1. Positive 1. So f prime of 1. Okay, and when I plug this in, we are going to get, again, a negative e to the negative second times, would there be a negative 3 again? So a negative 3, that's also a 3. Okay, so that becomes a positive, so our function's increasing. Okay, so I know that this is a max, and I know that this is a min. So we go ahead and plug those in. So our relative max, Okay, and I'm gonna plug those into our actual function. So negative 1/2, comma, and when I plug it into my function here, I get a positive 1/2 times e to the power of, I believe it's negative 1/2. Okay, there's our max, and then our relative min is going to be, so I plug in positive 1/2, and I get a negative 1/2. Hold on. Sorry, this is positive 1/2. I plug in 1/2, and when I plug in 1/2, my output is a negative 1/2 e to the power of negative 1/2. Okay, so there you have it. That is differentiating exponential functions, and then also some applications finding maxes and mins. Catch you next time. Peace.